Well, hi again. This is Bob, and we're getting ready to take a look at the last lesson in Chapter 8, and it deals with the chi-squared test for variance or standard deviation. And as always, you may recall that in Chapter 7, we introduced the idea of intervals based on chi-squared, confidence intervals. And we learned how to use the tables, but we learned how to use the tables for two-tails. And as you may have discovered or may understand now, that there is such a thing as a two-tailed test when we're dealing with chi-squared tests and z-tests and t-tests and so forth. But there's also a right tail and a left tail test. And so that's why the book is starting out on page 461. They give us some reminders about chi-squared values on the top of the page. This, I'll leave most of the reading for you, but they remind us that chi-squared values must be greater than or equal to 0. In other words, the ones that we're going to deal with are going to be positive. And the family of curves based on degrees of freedom, which we've seen before. The area under the distribution is 1, and they remind us that they're positively skewed. And then they go through pretty much the same thing that they've given us, and we'll have a procedure table shortly, we've got to find the area under the chi-squared distribution, and they remind us about table G back on page 782, where we have our values. So what we have to do, and by the way, the first few questions, or the first few examples that we're going to look at, because the examples speak to the types of homework problems we're going to be doing, but the first 3 examples just basically deal with learning how to use the right, the left, and the two-tailed, or finding the right, left, and two-tailed chi-squared values. And we already know how to do the two-tails, but we'll go ahead and review it again just to make sure. So I'm at the kind of 2/3 of the way down on page 461, and I'm just looking at example 821. It just asks us, it's my pen here, it just asked us to find the critical chi-squared value, 15 degrees of freedom. All right, we don't really need to know that n was 16, but it is. And we've got an alpha of 0.05. Okay, and we're supposed to find, and they remind us that the test is right-tailed. As always, it's so helpful to draw a little picture. And this is different when we have a right or a left-tailed test. Okay, now this is a right-tailed test, so obviously our critical area is going to be on the right of our distribution. So this will be 0.05, and this will be 0.95. Okay, our non-critical area. And of course, what we're looking for is this cutoff value here. And by that, I mean it's the value that separates the non-critical from the critical area. So if you go up to look on the top of the very next page, 462, you can see that they go to degrees of freedom 15. We can read this directly. We do not have to, if you recall, for two-tailed test, we had to cut the alpha in 2, but we don't. We can use it directly, and you can see that it's 24.996 on the next page. Now, in just a couple of minutes, they're going to give us the chi-squared test. Remember, we have a z-test and a t-test, and we've got a population proportion test for what we're dealing with hypotheses testing. And so we're going to have a chi-squared test also. And just as a reminder, again, the last test that you'll be taking is just on Chapter 8, and it deals with, it's an open book test. Anyway, we get a little break on example 822 also, because this happens to be a left-tailed test with 10 degrees of freedom. And it turns out we can read this directly also. And what I mean by that is that we do not have to cut the alpha in two. Oh, excuse me, I forgot to put the alpha there, alpha 0.05. But what we do have to do, because this is a left-tailed test, we'll have to do the drawing because that always helps. We go 1 minus 0.0, shoot. I don't know why this pen keeps giving out, but okay. So here's our situation. And here's our critical area of 0.05. Okay, and recall down at the bottom here, when we're on the other side of the table, and by that I mean recall the table, as I've mentioned before, it has an alpha about in the middle there on the top of the table. You can see this one at the bottom of page 462. And notice that I'll exaggerate just a little bit. The values are complements of each other. In other words, you'll see a 0.05, and then equidistant, you should see a point. This is really acting up today, a 0.95, etc. Anyway, to get into the left table, to the left side of the table, and again, this will be all open book, you have to subtract the alpha from 1, recalling their complements of each other, and you'll notice when we're on the left side of the table, you have to access it using the complement, and they have 3.940 is our critical value. I may have to start all over again because this pen is really acting up today. Or sometimes it's just the blackboard collaborate. Anyway, we're going to finish off on this, reminding us how to use the tables. And of course, in the homework, I've given you questions that before you even start the homework, get you comfortable with the tables. And of course, you can check those answers in the back of the book and in our student solution manual. Anyway, the last one is the one we should be most familiar with, and it's example 823. And we have 32 degrees of freedom, and we're at alpha again, 0.05. And in this case, it's a two-tailed test. Okay, so this should be a bit of a review, but I'll first draw what we've got here. And I think I'll wait. Well, I'll just go ahead and, just so we know, or I did that backwards. 1 minus 0.05, shoot, equals 0.95. And so what that means, and there's more than one way to do this or explain this, but it means that we've got 95% in the non-critical, or 0.95 in the non-critical, and then remember we had to take alpha and divide it by 2 for a two-tailed test. So alpha over 2 would equal 0.05 divided by 2, or 0.025. So in the tails, we've got 0.025 and 0.025 in the right and left tail. And notice that the whole area now adds up to 1. Now, there's several ways that you can come up with the 0.0. Well, there's only one way to come up with that. But remember, when they say alpha is 0.05 and we have two tails, that means that that 0.05 must be divided into, cut in half, the same amount into each tail. And of course, it's also obvious that we're dealing with the 95th we want to be 95% sure when we're dealing with our determination to reject or not reject. Anyway, if you notice, and I think I followed their explanation pretty close there, you would go to 32 degrees of freedom, and you would run across on the table, and you may want to go back to page 782 to verify this, and on the small end, the left side, you get 10.982 for the critical value, and on the right side, you should get 36.781. Now, it's important to mention here, and we have an example that'll show us this, but in order for us to reject the null hypotheses, we must get a value, and remember, all chi-squared values are positive. We must get a chi-squared value less than 10.982 or greater than 36.781. Okay, well, in the middle of page 463, and again, you can read through this, but we have the same three tests when we're dealing with standard deviations or we're dealing with variances as we do for z-tests and t-tests and the population proportion test. Okay, they're the exact same, and they've written for the right tail and the left tail and the two tails, and of course you can refer to this for the quiz and the test. They've written the null hypotheses and they've written the alternative hypotheses. So what we want to concentrate in is this last formula that we're going to deal with, and it's the formula for a chi-squared test for a single variance. Or excuse me, yeah, for a single variance. And it's basically the degrees of freedom, which we've seen before, which is n minus 1, times the sample variance divided by the population. The population variance. Now, there's some little things we need to be aware of here. We must read the questions carefully to see whether they are going to see the information they give us. In other words, you will notice that both the when we're talking about the sample variance and the population variance, those are represented by squares. Now, if they happen to give us the sample variance, it must be squared in the formula. Or if they give us the population variance, it must be, excuse me, if they give us the population standard deviation, it must be squared. So that's a place we have to be careful, and they emphasize that in one of the examples. I'm going to work all three of the examples, and I'd like you to read over on the top of page 464. It's basically the same stuff that we've seen before for other testing situations. The only thing that I think I mentioned this several chapters ago, but it's I think it's about a little more than halfway down on page 464. They discuss why is it important to test variances. And they they remind us about, or they give us some different situations there where consistency is required, like in manufacturing. In other words, they mention when bolts are manufactured, you have to be careful with the variance in diameters, and that must be kept to a minimum, or else the nuts won't fit on them. My pet peeve is sometimes when I drive, I drink coffee, and of course, sometimes the lids for the supposedly for the appropriate size are either too tight. In other words, you have to force them on, or they're too loose, and then they can dribble while you're driving. Of course, another example of that we saw way back in chapter 3 when we were talking about the standard deviation. We were talking about two paint samples, A and B, and how their length of how their average life could be the same, but their standard deviations could be different. Okay, and then they give some other reasons there, but this is the reason that we, or some of the reasons, or the idea behind testing variances. Anyway, we'll look at 824, which talks about an example 824, which talks about an IQ test. And we've got a psychologist wants to see if the variance in IQs of 10 of her counseling patients. Recall, if I'm doing these by myself, the first thing I do is when I get a piece of information, I write it down. Everybody has their own way of doing it, but it sort of helps me understand the question to get the numbers out there. And then it tells us that she believes that it's less than the variance of the population, or she's testing to see if it's less. That'll be our claim, which is 225. So right away, we know that the population, and notice that they use the word variance, so that won't have to be squared, is 225. And then they tell us that now they've given us the sample variance of her 10 patients, which was 206. Okay, so recall that in this case, they have given us sample variance and population variance, so those do not get squared. Had they given us, for example, the sample standard deviation, then we must square that for the formula. Well, I might as well go ahead now, and I'll do the work on the next side. But our our null hypotheses would be that the variance is equal to 225, and the psychologist believes or is testing the claim that her patients would be 10 patients would be less. Okay, so the next thing I forgot to write the alpha. In this case, we're testing this at alpha 0.05. So once I get the information, and it's a little crowded on this screen here, but the next thing I do is I like to draw, I've got all the information I need for my formula, but remember on a left-tailed test, at alpha 0.05, we just saw this, that of course means that 1 minus 0.05 or 0.95 will be non-critical, and then 0.05 will be in the critical area. And we need this value here. And if you just go back a page, actually I'll point you exactly where we need to go back. The left-tailed test example was example 822, and we have to go look on the left side of the table where we see 0.95, and then drop down to see where we have degrees of freedom equal to 9. Excuse me. And that critical value turns out to be 3.325. Okay, so now I think I've got everything I need to follow along with their formula there. But again, if you can't come up with the critical value, you still make, in other words, you need the critical value in order to determine whether we're going to reject the null hypotheses or not. Okay, and I may have forgotten to write claim there, I just noticed, so I'll go back and do that now, just for completeness. Okay, so recall we've got our degrees of freedom, and I'll go ahead and write that as 10 minus 1 there, even though we know it's 9. And that gets multiplied times our sample variance, which is 206. So you do not need to, or certainly don't need to square that, and then the whole thing gets divided by the population variance. They've given us a variance, so it's not squared of 225. Well, that's just 9 times 206 divided by 225, which is 8.24. Now, we'll just refer to this here. You know, I'm glad I don't have much left in the way of lessons, because I'm going to have to buy, I believe, another pen, if that's indeed the problem. Okay, so we had 3.325 as our critical value, which set off our alpha of 0.05. And our test value was 8.24. I'll emphasize a little more. Now, 8.24 is not less than 3.325. It's obviously not in that critical region there, so that means that we're not going to reject the null hypotheses. Or said differently, because they use the term claim, there's not enough evidence to support the claim that the variance over 10 patients is less than 225. Okay, well, let's take a look at 825, which is a question about outpatient surgery. And they've given us the values there. It looks like we've got 3, 6, 9, 12, 15 different hospital administrator believes the standard deviation of the number of people using outpatient surgery per day is greater than 8. Okay, now the first thing I notice when I see that is that they're using the standard, they're talking about the population standard deviation is 8, but remember, and this is probably the most important thing where we could go wrong using this new formula, remember, when we get around to the actual work, we're going to have to square 8 because they gave us the population standard deviation, and the formula calls for the variance. So we're just going to have to square 8. Okay, then they tell us a random sample of 15 days is selected and the data is shown. So n equals 15, and of course that's degrees of freedom 14, because we've got to come up with a value. And it tells us that the hospital administrator believes that it's greater than 8. Okay, so we might as well set up our hypotheses now as we go. And they've given us the hypotheses there, as you notice, in terms of the standard deviation. So again, I remind everyone we're going to have to square that. Okay, and then the last couple of things we know is that alpha is 0.10, but it's a right-tailed test, so we can look that up directly. And then the last thing we need to know is the fact that where's that at here? A random sample of 15 days is selected. The data are shown. Okay, well, what they're not showing us here is they took those 15 days and they have found out I'm looking for the value. They found out that the Well, I guess they perhaps assumed that we were going to find, oh, I see it in step 3 there. Go back, although we're not going to do that. If we went back to chapter 3, and if we had taken the time to find the sample standard deviation, we would have found out that it's 11.2. But that's more work than the entire problem, and I remind everybody that we don't need to do that. We're going to concentrate on the skill at hand, and you will not have to, I'll give you all the variables or all the information that you need to plug in to a formula. There won't be an even greater challenge by having to go back and figure a standard deviation or something like a sample mean or something like that. So here's our situation now. Remember, the alpha was 0.10. It's a right-tailed test, so that means that 90% of the area is non-critical, and 0.10, and I'm showing us our our critical area there. And we had degrees of freedom 14. So we can go, and it may not be a bad idea to just go back to page 461, and you can then go on the top of page 462 and see the value associated with 0.10 on the right side of the table there, and it turns out to be 21.064. Remember, the right and left side, or right tail and left tail, access the table differently. Okay, anyway, we finally get down to the point where we've got all the information we need, and so we put the chi-squared test on it now. But remember that both the sample standard deviation and the population standard deviation must be squared in the formula. So 11.2 was our sample standard deviation. It must be squared. And our population standard deviation was 8. That's why they have 64 down there. Actually, I think I'll prefer to write it this way. Okay, instead of just writing 64, I'm going to write 8 squared, which is 64 for clarity. And we end up with a calculated chi-squared value of 27.44. Clearly, 27.44 is larger than or greater than 21.064. In other words, we're further into the critical area there, so we're going to reject the null hypotheses. Or as the book says, there's enough information to accept the claim or support the claim. All right, we might as well finish off by doing the two-tailed test, and that's on the top of page 466. And this is about nicotine content of cigarettes. And we've got a cigarette manufacturer who wants to test the claim that the variance of the nicotine content of its cigarettes is 0.644. Okay, well, what I'm getting from that is two things. One, that that's going to be the claim, but they've given us the term the variance. Of course, we're talking about the population variance. And then our alternative hypotheses, would be the variance, is not. Notice when we read the question, they're just testing the claim. The researcher is not saying that it's greater than 0.644 or less than 0.644. They're just testing the claim. In other words, the true variance could fall on either side of our chi-square distribution. All right, well, they go on to tell us that now here we have to be careful. Nicotine content is measured in milligrams, and assuming that it is normally distributed, a random sample of 20 cigarettes and had a standard deviation of 1 milligram. All right, well, in this case, when we square 1, we're still going to get 1. But what I'm emphasizing again, because this is a place where it's very easy to make a mistake. Oh, excuse me. I'm looking. I got off a little track there. Where are we at here? We should test the variance. I think I just may have miscopied something here, or looking at two different problems at the same time. No, we're fine. Okay, it's just a matter of making sure that I'm not confusing one part of the problem with another. Okay, yes, indeed. What I was trying to point out here, we know that they've given us the population standard, the population variance, but what they've given us for the sample variance is 1 milligram, and normally, well, we always have to square that. But in this case, when we square 1 or 1.00, it's still going to equal 1. And I'm sorry my pen is bleeding there. But if you look when they set the formula up, notice that even though 1 times itself is 1, they've still written it as 1 squared. So I got just a touch ahead of myself there, but we'll fix it up now. By saying that our alpha is 0.05. I'm just trying to finish this lesson without completely starting again because my pen is acting up a little bit. Anyway, this is a good question because it forces us to review how we find the critical values, and we'd start off, or one way to start off would be to find out the area in the non-critical region, which would be 0.95. Okay. And then remember, for two-tailed test, we must find alpha over 2, and that would be 0.05. If I write slower, maybe I can get it to work a little better. Okay. Now, we've been here before. This is the critical regions. But recall what we must do. We must, to get into the tables, we must subtract that alpha over 2, which is 0.025 from 1, and we end up with 0.975. So the two values that we get into the tables with, or in other words, our critical values, are going to be associated with 19 degrees of freedom, because remember, N was 20. And we're going to be using 0.025 and 0.975. Now, this is stuff that we did in Chapter 7, And when we finally go back to 19 degrees of freedom and go vertically up to find out what values are associated, come vertically down and across, we're going to end up with 0.89 or 8.907 on the left side and 32.852 on the right. Those are our critical values. And I'll see if I can clean that up just a little bit. If you have any doubt on how to get the values, then you can just go back to Chapter 7, because this one we've done before for two-tailed. Okay, we're finally ready to calculate the chi-squared value. So we had a sample size of 20, and we want to go with degrees of freedom. Remember, our sample standard deviation was 1, but they square that in the formula, even though 1 squared is 1, because the formula calls for the sample variance squared. And on the bottom, the established, notice in the question, they told us that the variance for the population was 0.644. So variance is 0.644. That is not squared. And then finally, when they compute chi-squared, they end up with 29.5 milligrams. All right, and of course 29.5 would not be in the critical region. I'm just very frustrating here, but I'm going to try to finish it off. I'm sure you can see the conclusion here, but our test value of chi-squared equals 29.5 is not in the critical region there. It lies outside of the critical region. In other words, 29.5 is less than 32.852. And it's bigger than 8.907. So it does not lie in either critical region, and therefore we can make a summary of not reject the null hypotheses. Or said differently, there's not enough evidence to reject the manufacturer's claim that the variance of the nicotine content of the cigarettes is equal to 0.644. Okay, so the important thing for me is that we won't be rejecting the null hypotheses. I'm going to try to figure out what's going on with my pen. It may just be the Blackboard program. That happens from time to time. But we've got another lesson here because we're going to continue on with this chi-squared, but what we're going to do, as we've done with the Z, or I should say with the T test and the Z test, but we're going to convert our chi-squared values to p-values, and of course, like with the t-test, we'll end up with an interval, and I thought it would be best to approach that as a separate lesson, so I'll be back shortly with the changing our chi-squared calculated values to p-values, and then determining whether to reject or not reject. So I'll be back shortly with that. Thank you.